Welcome to the next session of Subject Engineering Maths. We were discussing Chapter 5 Probability. In the last session, we were in the middle of types of functions and we have finished one function. Next category of function is onto function. This is also called as surjection. Suppose we have a function f from a to b. We say that this is onto if every element of codomain has at least one premise in A. We have a function f from a to b. We say that this is onto if every element of B has at least one premise in A. So this is if every element of B has at least one premise in A. In that case, the function is said to be onto function, or it is also called as surjective function. Let us see an example. Suppose we have a set A, for example 1, 2, 3. Suppose B, the second set B is alpha, beta. Now 1 is set to alpha, image of 1 is alpha, image of 2 is alpha, image of 3 is beta. So this is an example of onto function. Alpha has at least one premise, beta has at least one premise. Therefore, this is called an onto function. Suppose when you look at this, suppose the first set contains, for example, 1, 2, 3. Second set contains, for example, alpha, beta, gamma, say, for example, delta. Now, image of 1 is alpha, image of 2 is beta, image of 3 is gamma. So, in the worst case, 3 elements can be mapped to 3 different elements of second set. But in this case, delta is kept 3. So, therefore, in this case, delta has no premise in A. Therefore, this is not an onto function. This is not onto function. That means if you want to construct onto function between two finite sets, the number of elements in A must be greater than or equal to number of elements in B. A is a finite set, B is a finite set. So finite set means it is having limited number of elements and B is also having limited number of elements. So in order to construct a onto function between A and B, the number of elements in the first set must be greater than or equal to n. Here you can see we have 3 elements, 2 elements. Here 3, 4. You can have maximum 3 elements. But here one element is excess when compared to A. Therefore, we are getting function but not onto. Therefore, if you want to get onto function between two finite sets, the number of elements in the first set must be greater than number of elements in the second set. But in case of 1-1 function, the number of elements in first set must be greater than less than or equal to number of elements in the second set. A is one set, B is codomain set. This is a domain set and this is codomain set. If you want to construct 1-1 function, the number of elements in A must be less than or equal to B. Why it is so? Because M elements can be mapped to different M elements. So if I have 5 elements, to get 5 different images for these 5 elements, I must have minimum 5 elements in the second set. It may have extra when compared to 5. But if it has M elements, to set M images to all the M elements, I must have minimum M elements in the second set. Therefore, to get 1-1 function, number of elements in A must be less than or equal to number of elements in B. But whereas in case of onto function, it is reverse. Number of elements in A is greater than or equal to number of elements in B. And this is the definition of onto function. Okay, write the definition. Onto function. In brackets, you write surjection. A function f from A to B, a function f from A to B is said to be onto. A function f from A to B is said to be onto if every element of B has at least one premise in A. A function f from A to B is said to be onto if every element of B has at least one premise in A. So write this example. This is example 1. Anyhow, this is onto function. Example 2, this is not onto function. This is not onto because delta has no premise in A. Note these two examples. One is positive and B are two sets having 4, 2 elements respectively. So A is a finite set having 2 elements, B is a finite set having 2 elements. Number of elements in A is greater than or equal to number of elements in B. So certainly we can define onto function between A and B. That is very clear. Now the total number of functions is total number of functions from A to B is 4 square. This is 16. Now my question is, out of these 16 functions, so this is 2 power 4. So here 2 elements, here 4 elements. This is 2 power 4. It is 16. So out of these 16, how many functions are onto functions? Let us see. Suppose A, here assume that A and B are, for example, 4 elements. So in this case, the number of elements I assumed as alpha, beta, gamma, delta, and beta, so only 2 elements A, B. Now let us see how many onto functions. Total number of functions from A to B is 16. Now suppose I define one function f1. Alpha is set to A, beta is set to A, gamma is set to A, delta is set to A. Now this is not an onto function because B has no premise. I will define one more function like this. So this is A and this is B. I call second function as f2. So this is alpha, beta, gamma, delta, AB. Now the alpha is set to B, beta is set to B, gamma is set to B, and delta has image B. Now this is not onto function. So both are not onto functions. In this case, A has no premise. In this case, B has no premise. Basically, both the functions are called constant functions. Both the functions are called constant functions because all elements are set to single image. All elements are set to fixed image. So in this case, B has no premise. In the second example, A has no premise. So in both the cases, they are not onto functions. Except these two. Except these two, in the rest of the cases, A will have at least one premise, B will have at least one premise. Therefore, except these two, rest of the functions are onto. Therefore, the number of onto functions is 2 power 4 minus 2. So therefore, the conclusion is, if A comma B are two finite sets having m comma 2 elements respectively, where m is greater than or equal to 2. In the first set, the number of elements is minimum 2, but second set is having exactly 2 elements. Exactly 2 elements. In the first set, you can have any number of elements, but that is greater than or equal to 2. In that case, the total number of onto functions from A to B is 2 power m minus 2. Note this point. Note, if A comma B are two finite sets, if A comma B are two finite sets having m comma 2 elements respectively, if A comma B are two finite sets having m comma 2 elements respectively, where m greater than or equal to 2, if A comma B are two finite sets having m comma 2 elements respectively, where m greater than or equal to 2, then the number of onto functions from A to B, then the number of onto functions from A to B is 2 power m minus 2. Is 2 power m minus 2. To justify this, you can have this example. Of course, this is m value in this case, but the number of elements in the second set is 2. So you write this discussion so that you can understand how it is coming 2 power m minus 2. Suppose A is a finite set, B is a finite set having m comma n elements respectively, where m is greater than or equal to n. Number of elements in A is m, number of elements in B is n, where m is greater than or equal to n. Then the total number of functions onto functions from A to B is given by the expression sigma k equal to 0 to n minus 1 whole power k into nc n minus k into n minus k whole power m. So this expression gives the total number of onto functions between two finite sets A and B having m comma n elements respectively. You simplify this, you will get some expression. You can see here we have combinations. See, for when you take k value even number, you will get plus. When you take k value odd, you will get minus. That means we were considering few functions and we were neglecting few functions. So there is some gain and there is some losing. Now let us see how to get this function. I will start with a simple example. Suppose in the first set we have four elements: alpha, beta, gamma, delta. Suppose B, we have for example three elements, 1, 2, 3. Here four elements, here three elements. Now let us see how many onto functions are possible from this set to this set without this expression. I go for generalized way. After that I will compare this result with this. Okay. Now you can see here what I am doing is, here I am fixing alpha comma beta to 1. Alpha and beta are set to 1. So the images of alpha and beta are 1. But gamma and delta can be set to 2 and 3. Suppose like this. So that means the images of gamma and delta are 2, 3. Another possible case is the images of gamma and delta are 3, 2. So this is one possible mapping. This is another possible mapping. Here images have been reversed. But in this case, alpha is set to 1, beta is set to 1. Gamma is set to 2, delta is set to 3. This is one function and this is another function. So totally we are getting two functions. We were getting two functions. So similarly, if I set alpha comma beta to 2, alpha and beta are set to 2. Now beta comma, now in this case gamma comma delta, they can be set to 1, 3, or alpha gamma gamma, they can be set to 3, 1. Again we are getting two functions. Again they were getting two functions. Next time I will set alpha comma beta to 3. Now beta, gamma and delta can be set to 1 and 2 only. So therefore gamma, delta, they can be set to 1, 2, or gamma, delta, they can be set to 2, 1. In this case again we were getting two onto functions. Two onto functions. That means what I am doing is, I have selected two elements in the first set. Even I will tell you why particularly you are selecting two. Let me tell you reason after some time. But in this case, alpha and beta are set to 1. So here two elements are kept free. Here two elements are kept free, so that I will get arrangements very easily. So to get, if I free equal number of elements in A and B, my arrangements will be so simple. So that is the only logic. So therefore here gamma and delta are set to 2 and 3. Therefore alpha and beta are fixed to 1. So alpha and beta are fixed to 1. Then gamma and delta can be set to either 2 and 3. So image of gamma delta, image of delta 3. Or in the next case, images will be reversed. So when alpha and beta are set to 1, then gamma and delta can be set to 2 and 3 in two different ways. So similarly, if alpha and beta are set to 2, then gamma and delta can be set to 1 and 3 in two different ways. Like this, if alpha and beta are set to 3, then gamma and delta can be set to 1 and 2 in two different ways. Therefore, with alpha comma beta, if I fix alpha and beta to two different elements, I am getting totally 6 functions. So in this case, we were having two functions, two onto functions and two onto functions. So when two elements are fixed to one element at a time, I will get totally 6 onto functions. Next time, if I will repeat the same process for alpha gamma. Again I will get 6. Next time I will set this for alpha delta. Again this will be 6. Next I will repeat the same process for beta gamma, 6. Beta delta, 6. Next to gamma delta. Again I will get 6. Therefore total onto functions is, total number of onto functions is 36. Basically this 36 is nothing but, you can see these are nothing but 2 elements subset from 4 elements. So we were selecting two elements, alpha, beta, alpha, gamma, alpha, delta, beta, gamma, beta, delta, gamma, delta. That means at a time we were selecting two elements from the domain set. So you select two from four elements, 4C2. For each such combination, we were getting totally 6 functions. So this is 4C2 into 6. Now you can see we were getting combinations. So because of this reason, so NC n minus k. So therefore in this case the result is 36. Therefore this is the general formula. If A comma B are two sets having m comma n elements respectively, where m greater than or equal to n, then the total number of onto functions from A to B is given by the expression sigma k equal to 0 to n minus 1 whole power k into nc n minus k into n minus k whole power m. So first let us write this note. After this you can have this example. Note, if A comma B are two sets, if A comma B are two sets having m comma n elements respectively, if A comma B are two sets having m comma n elements respectively, where m greater than or equal to n, if A comma B are two sets having m comma n elements respectively, where m greater than or equal to n, where m greater than or equal to n, then the total number of onto functions from A to B, then the total number of onto functions from A to B is given by this expression. So if it is over, you start with this example. So like this, for each combination 6, so totally like this you will have this. 2. Third category of functions, that is bijection. Earlier we have seen two types of functions. One is injection and another is surjection. Here bi means two. So we need to work out with two sections. So a function which is both injection and surjection is called a bijection. A function which is both injection and surjection, or simply a function which is both 1, 1 and onto is called a bijection, right? Now if you want to get 1, 1 function, the condition we have is m less than or equal to n. For onto function, m less than or equal to n. But this and this must be required for bijection. Therefore, to form a bijection between two sets, they must have equal number of elements, right? Therefore, let us see an example. Suppose A has 3 elements 1, 2, 3. Suppose B has 3 elements alpha, beta, gamma. Now both have equal number of elements, so bijections are possible. How many bijections are possible? Let us see. So 1, 2, 3. Image of 1 is alpha, image of 2 beta, image of 3 gamma. Next alpha, gamma, beta. So beta, alpha, gamma, beta, gamma, alpha, gamma, alpha, beta, gamma, beta, alpha. So all these are possible permutations with the 3 symbols. So therefore we have totally 6 functions. All these are bijections between two finite sets. So therefore when you have equal number of elements, the total number of bijections is 3 factorial. All these are arrangements of 3 symbols. So in 3 factorial ways, that is 3p3. 3p3 is, actually this expression is 3p3. So this is exactly 3 factorial. So when both sets A and B have equal number of elements n and n, then the total number of bijections between A and B is exactly n factorial. Okay, very simple issue. So write the definition. A function which is both 1, 1 and onto is called a bijection. A function which is both 1, 1 and onto is called a bijection. Example, you can have this followed by this. First you have this and then these permutations. Note, if A comma B are two finite sets, if A comma B are two finite sets having m comma n elements respectively, if A comma B are two sets having m comma n elements respectively, then m equal to n. If A comma B are two sets having m comma n elements respectively, then m equal to n in order to define a bijection from A to B. In order to define a bijection from A to B. One more note. If A comma B are two sets, if A comma B are two sets having n elements each, if A comma B are two sets having n elements each, then the total number of bijections from A to B, then the total number of bijections from A to B is n factorial. Then the total number of bijections from A to B is n factorial, right? Now with this, we have finished all basics of probability. I mean basic definitions, examples, till random variables, discrete random variable, continuous random variables, expectations, variance, standard deviation and properties, etc. Even functions concept also. Now let us move to classroom workbook based on basic concepts of probability, random variables and functions, right? So go through classroom workbook. So we start with the classroom workbook from question number 1. The random variable x has a probability distribution function p of 4 equal to 1 by 4, comma p of 8 equal to 1 by 4, comma p of 12 equal to 1 by 4, comma p of 16 equal to 1 by 4. The expected value of x is options 1, 3, 10, 12. Let us handle this. So a random variable x has a PDF like this. So what are my sample points? 4, 8, 12 and 16. So let us have PDF in the table format. So x values are 4, 8, 12, 16. The respective probabilities are 1 by 4 each. 1 by 4 each. Now when you look at this PDF, it contains only finite number of sample point 1, 2, 3, 4. Therefore it is a discrete random variable. So the expected value of x, E of x equal to sample point into probability. So 4 into 1 by 4 plus second point 8 into 1 by 4 plus 12 into 1 by 4 plus 16 times 1 by 4. Because it is a discrete random variable, so PDF is given by summation sigma I equal to 1 to n xi into p of xi. So therefore this is 1 plus 2 plus 3 plus 4, it is 10. So option C is right answer. For the function f of x equal to a plus bx, comma 0 less than or equal to x less than or equal to 1 to be a valid PDF, then the values of a comma b is, options are given. Now look at this. So here PDF is given in terms of x. Now this is a general sample point. Here x is ranging from 0 to 1. That means x is taking infinitely many sample points. So see, whenever PDF is given for individual sample points, that comes under discrete random variable. If a PDF is given as a function in terms of x, ultimately it confirms that the random variable x is a continuous random variable. So how to distinguish that whether it is a discrete random variable and continuous random variable? Simple issue. if a probabilities of sample points are mentioned very clearly. In the previous question, P of 4, P of 8, P of 12, P of 16, for individual sample points, probabilities are mentioned. In that case, it comes under a discrete random variable. If probabilities of all sample points are defined by a single function in terms of x, then it refers to continuous random variable. Therefore, this is a PDF who a plus bx, but actually x is ranging from 0 to 1. If it is a valid PDF, then what are the values of a and b? Now let us see. Since f of x is a valid PDF, implies integral minus infinity to plus infinity, f of x dx must be equal to 1. But here f of x is defined only from 0 to 1. Therefore, the limits will be restricted to 0 to 1. So, integral 0 to 1 f of x dx equal to 1. So, this implies integral 0 to 1 f of x is a plus bx. So, integral 0 to 1 a plus bx dx equal to 1. Therefore, this implies integral a is ax plus integral bx is bx square by 2, but limits are from 0 to 1. So, apply the limits, we get a plus b by 2 equal to 1. Now, I have a single equation. This is a single equation in two unknowns a and b. So, it possesses infinitely many solutions, but look at options. In the first option, it is 1 comma 4. So, replace a value 1, b value 4, you won't get 1. So, this is not a right choice for a and b. Now, let us go to option b. So, the values are 1 by 2 comma 1. So, replace a value 1 by 2, b 1, 1 by 2 plus 1 by 2, 1. So, it satisfies this. Therefore, the value of a is 1 by 2 and the value of b is 1. So, option b is right answer. Let E comma F be any two events with P of E union F equal to 0.8, P of E equal to 0.4, P of E slash F equal to 0.3, P of union F is 0.8, P of E 0.4, P of E slash F 0.3. Then what is P of F? So here options are given. Now this question is related to conditional probability. You need to apply conditional probability as well as addition theorem on probability. Now let us see. Let us apply addition theorem on probability. At first, P of E union F is P of E plus P of F minus P of E intersection F. Now here P of E intersection, actually P of union F is 0.8. So 0.8 equal to P of E is 0.4 plus P of F minus P of E intersection F. Therefore, from this P of F minus P of E intersection F equal to 0.8 minus 0.4, this is 0.4. Now we need to simplify this. So here conditional probability is given P of E slash F. P of E slash F is given as this value is 0.3. But by condition probability, this P of E slash F is P of E intersection F divided by P of F. This is given as 0.3. Therefore, P of E intersection F equal to 0.3 times P of F. Therefore, in place of this P of E intersection F, we can write 0.3 times P of F. Therefore, from this equation, we can write P of F minus this P of E intersection F is replaced by this 0.3 into P of F equal to this is 0.4. So, therefore, this is 0.7 into P of F equal to 0.4. Therefore, P of X equal to 0.4 by 7. So, this is 4 divided by 7. So, option B is right. So, in this problem, we have used two things. One is the definition of conditional probability and another is addition theorem on probability. Work out this. Now, let us move to question number 4. Two dice are thrown simultaneously. So how many sample points we get? 6 square, 36. The probability that the product of the numbers appearing on dice is a perfect square. When two dice are thrown, you will get two outcomes. Multiply two numbers, you will get some number. That number must be perfect square. So what is the required probability to get product as a perfect square? Now let us see, this is one sample point, 1 comma 1. 2 comma 2 is one sample point. 3 3 is one sample case. 4 4, 5 5, 6 6. Multiply these two, you will get 1 square. Multiply these two, 2 square. Multiply these two numbers, 3 square, 4 square, 5 square, 6 square. So all these are perfect squares. And there is another possible case, 1 comma 4, 4 comma 1. So when you multiply these two, you will get 4. 4 is 2 square. Multiply these two, 4. 4 is 2 square. So these are the sample points where when you multiply these two outcomes, the result is a perfect square. So how many sample points? Totally 8. So 8 sample points out of 36. So therefore 4 2s, 4 9s. So the required probability is 2 by 9. So option B is right answer.